Section: Quantitative and Qualitative Intelligence. In this section, we explore how to evaluate the intelligence performance of large language models, LLMs, by dividing the assessment into two main categories: quantitative intelligence and qualitative intelligence. When we talk about quantitative intelligence, we mean the model's ability to store data and effectively use and remix that information, similar to how humans possess knowledge. On the other hand, qualitative intelligence involves the model's capacity to analyze, judge, and draw conclusions from that stored data and new information. At first, this distinction might seem straightforward, especially when we think about human intelligence. However, there is currently no standardized way to evaluate intelligence in LLMs and similar AI systems. Quantitative intelligence encompasses the various areas of expertise that an LLM can cover. Since these models are trained on vast amounts of data, primarily sourced from the internet, their quantitative capabilities are extensive. We can engage in reasonable conversations with an LLM in many languages, discussing topics ranging from knitting to ancient literature to quantum physics. At this point, these models likely have access to more information than any individual human. To assess quantitative intelligence, we should conduct systematic tests that cover a wide range of topics and varying levels of detail within those topics. The quantitative measures we use depend directly on the training data and highlight the areas where the model specializes. Additionally, understanding the quantitative capacity of a model helps us determine whether its output is merely a rearrangement of training data or if it is genuinely derived from context. Unlike humans, LLMs do not experience issues with concentration or motivation, allowing for a more extensive evaluation. Instead of relying on a few questions like in traditional tests, we can analyze a model using hundreds of thousands of questions and tasks in a relatively short time, provided we have a comprehensive question catalog that spans everything from elementary school knowledge to university-level content. The factual accuracy of the model's responses, along with the metrics we gather across different topics and levels of complexity, paints a picture of the model's knowledge. The Massive Multitask Language Understanding (MMLU) test, which includes nearly 16,000 questions across 57 tasks, is a step in the right direction. However, it does not clearly differentiate between knowledge retrieval and problem-solving abilities. To thoroughly examine quantitative capabilities, we should focus on questions that emphasize information retrieval rather than reasoning, which should be evaluated separately in a qualitative test. Current methods for assessing human intelligence assume that if someone can complete a specific task, they can also handle similar tasks of equal or lesser difficulty. Whether this assumption applies to LLMs is still up for debate, and we refer to this as qualitative intelligence. Qualitative intelligence includes skills like reasoning, strategic actions, and drawing meaningful conclusions from data that the model has not encountered during training. This distinction is crucial because it helps us determine whether a model is simply rearranging known data or genuinely solving new problems, which is a hallmark of intelligence. Evaluating qualitative intelligence requires different examination techniques. However, the partially closed nature of some models and the vast amount of training data complicate this assessment. A notable example is the ongoing research into the persuasive abilities of LLMs in structured debates. By using randomized control trials, which are common in clinical research, we can evaluate the persuasiveness of machines compared to humans in both qualitative and quantitative terms. While we urgently need a gold standard for qualitative assessments of intelligence, such a standard is still lacking. Despite this, when we compare reasoning test results from specialized models, such as early transformer models, to current LLMs, we see only gradual improvements in qualitative measures, especially when considering the significant increases in model size and training data over time. For a fair comparison of general reasoning capabilities among models, we should separate the quantitative aspects from the evaluation. As we consider the exponential growth of training data and model size, we recognize that this trend may soon reach a limit in terms of data availability. For instance, if we imagine training a model on all the information available on the internet and every text ever written, we might wonder how intelligent such a model could become under the current self-supervised training methods, which predict words in sentences. Quantitatively, this model would encompass all human knowledge, and qualitatively, it could potentially surpass every individual who has ever lived, given its access to countless human ideas. However, we argue that this hypothetical qualitative advantage would still be limited because the model's training is fundamentally based on human thoughts and language. Similarly, a perfect model for the language of a specific animal species, like songbirds, would struggle to explain complex human concepts, such as Einstein's theory of relativity. The foundation of large language models is their training data, which reflects the cognitive abilities of the species they are based on. While LLMs demonstrate remarkable linguistic accuracy, it remains uncertain how this translates into broader cognitive capabilities typically associated with language. This raises the question of whether language alone is enough to develop such capabilities. Moreover, the ongoing debate suggests that merely reorganizing vast amounts of data may not be sufficient to produce results that mimic human behavior. Relating these ideas to the concept of superhuman AI, we see that current and future advanced LLMs can easily exceed human intelligence in quantitative terms, especially when AI tasks are combined with their typically short inference times. However, achieving qualitative improvements that are orders of magnitude greater than human capabilities seems unlikely or even impossible with current learning methods. Additionally, any truly emergent intelligence properties of these models might not be detectable with our existing evaluation measures. To effectively prove or disprove the existence of emergent intelligence in specific LLMs, we must pay close attention to both quantitative and qualitative intelligence measures. Developing frameworks that address these issues should be a priority for the research community. Even without a singular growth in intelligence, the societal impact of LLMs is already significant. As their quantitative intelligence increases, these models can be applied across various domains, potentially handling tasks that currently require teams with diverse expertise. In the future, a single LLM could initiate a new campaign, create a movie, or plan a medical study with just a simple prompt. These advancements are crucial for speeding up existing processes. However, access to groundbreaking technology or new physical concepts is not on the immediate horizon. Therefore, while the creation of uncontrollable superintelligence may not be the most pressing concern, we must be wary of large-scale job losses, misinformation, and election interference. In conclusion, the ongoing and future developments in LLMs will lead to models that encompass a significant portion of human knowledge, but they may not quickly surpass human qualitative output. To address this complexity and reliably assess emergent intelligence properties or even superhuman behavior, we should evaluate the intelligence performance of models using separate quantitative and qualitative intelligence metrics.